in this video, we will try to find the time periods for simple harmonic motion for various geometries. So in this particular case, the first case, we have a rod of length L that is fixed at a pivot point, and it rotates about the pivot point. Okay, and that pivot point is at a distance x from the center of mass, right? So we want to find out what its time period of motion is, right? So what we will do here is we will write the equation for torque. Okay, the torque here, torque equals I times alpha, right? And since this is a restoring torque, okay, we will write this as a minus sign times the force times the distance of the force acting from the pivot point, and that is x. Okay. So here what happens is that the weight of the rod acts through the center of mass, and that's at a distance of x from the pivot point. So if you take the component of the force of the weight along the rod, it is clear that it's not going to produce any torque, and that component is mg cosine theta. So the force that provides torque is a component of the weight that's perpendicular to this rod, and that is mg sine theta. So we can write this as minus mg sine theta times x. Okay, and when theta is very small, when theta is very small, sine theta is approximately equal to theta. So this expression equals minus mg times theta times x. Now alpha is the angular acceleration, that is theta double dot. Okay? That's a second derivative of theta. So we can write here alpha, or rather I times theta double dot equals minus mg x times theta, or theta double dot equals minus mg x divided by I times theta, right? So, and the question is, what is I? I is the moment of inertia, obviously. So I here is the moment of inertia of the rod about the center of mass is 1/12 m times L squared plus m times x squared by the parallel axis theorem. By the parallel axis theorem, right? So let's put that in. We get theta double dot equals minus mgx divided by ml squared divided by 12 plus mx squared times theta. And so the nice thing here is that the masses cancel out on the numerator and the denominator, and therefore we are left with minus gx divided by L squared divided by 12 plus x squared times theta. Now we know that theta double dot equals minus omega square theta. Okay, and therefore omega equals gx L squared divided by 12 plus x squared, and we take the square root of that. And we know that omega is the angular speed is 2 pi radians divided by the time to traverse 2 pi radians, and t is the time period. So therefore t equals 1 over 2 pi L squared divided by 12 plus x squared, okay, divided by g times x, and we take the square root of that. So the interesting thing here, okay, is that you can find out t, okay, you can find out t as a function of x. Okay, t as a function of x, the time period. And so what you can do here is that if you want to find the minimum time period, okay, so you can do this del t or del x, okay, equals 0. Okay, so essentially that will give us 2 pi over square root of g, okay, is minus L square divided by 12x square plus 1, okay, divided by 2 times L square divided by 12x plus x to the power 3 or 2, and we set that to 0, so we get x equals L divided by square root of 12. Okay, and you can take the double derivative of this and satisfy yourself that the double derivative is actually positive. Therefore, when let me write this a little bit better. When x is equal to L divided by square root of 12, the time period is a minimum period is a minimum when x equals L divided by square root of 12. So the question also being asked is, okay, so what happens if L increases? Obviously, if L increases, the time period is going to increase. And what happens if the mass of the rod changes? So it's not going to affect the time period, right? Because the mass is nowhere in the picture in the formula for the time period. So this gives us one instance of how to compute the time period for one particular geometry. So in this example, we will find the time period of vibration of a pendulum. So this pendulum is a specific type of pendulum where we have a disc of diameter d, okay, that's suspended using a massless rod of length L, right? And there is a spring with a spring constant equal to k that's attached to the pendulum. So, and we want to find the time period here. So the restoring torque here is essentially has two components. So one component comes from the weight of the pendulum, which is mg sine theta, being the force, okay, and the distance of the force from the pivot point, it is L plus dO2, okay, and there is another contribution from the spring called k theta, and since both of these are restoring torques, we'll put a minus sign in front of them. And the torque is also equal to the I times alpha, which is equal to I times theta double dot. And when theta is small, sine theta is approximately equal to theta, right? So therefore, we can write this equation as I times theta double dot equals minus mg L plus dO2 plus k times theta, or we can write theta double dot equals minus mg L plus r, where r equal to dO2 plus k, okay, divided by I, okay, times theta. Okay, now so here omega square equals mg L plus r plus k divided by I, right? Okay. So therefore what we do here is let's take out the square from the left and put a square root on the right, okay, because so now what is I here equals half times mr squared, okay, because that's the moment of inertia of the circular disc, plus the distance of the circular disk, okay, center of the circular disk from the pivot point is m times L plus R square, right? So if we combine all the terms, we get omega here equals m times G L plus R plus K, okay, half m R square plus m L plus R square, okay, that's raised to the power of half. Now we want to see whether we've got the correct expression. So what we will do here, we will set R equal to 0, okay, and we'll set K equal to 0. So in that special case, we get omega equals mgl divided by m L squared. Okay, we take the square root of that. And so one of the L's gets cancelled out, the M's get cancelled out, equals G divided by L square root. And this is nothing but omega equals 2 pi over T equals G over square root of G over L. Therefore, the time period here equals 2 pi times square root of L divided by G, which is the time period of the pendulum. Okay. Assuming that the pendulum bob here, the pendulum bob has a very small radius. Okay, it's a very small radius, but it has a finite mass. Okay, so now we have now that we've recovered the classical formula for the time period, let's finish off the rest. So here omega we know as 2 pi over T, okay, equals mg times L plus R plus K, okay, times mr squared divided by 2 plus m times L plus R square, and we take the square root of that. Therefore, the time period, the new time period here, okay, is nothing but mr square plus times m plus L plus R squared divided by m g L plus R plus K. Okay, so that's the time period for the configuration when the radius of the bob is greater than 0. Okay, the spring constant is not equal to 0. Okay, so both of these are the case. Now the question is, okay, why would we do something like this? Is that if we have this kind of configuration, we can measure the time period, okay, using a clock. We can measure the time period using a clock. We know the mass of the pendulum bob, right? We know the acceleration due to gravity. We know the length of the rod. We know the radius of the pendulum bob. So we can compute the spring constant K here. So that's the interesting part in this problem. Okay. So I hope this gives you an insight into how to not only find the time period for this particular configuration, but also how to use it to find the spring constant K.